Our main topic today is continuing with series. Let's write down an example. The series n goes from 1 to infinity of, let's make it 2 to the n over n cubed plus 1. Now, when people typically see a series like this, their temptation is, okay, I need to get a little feel for what's going on. Let me figure out the first few non-zero terms. And there's certainly nothing wrong with that, though oftentimes it does take more time than you might have. If I start writing down the terms, using the formula for the terms, I get 2 to the first over 1 cubed plus 1, plus when n is 2, 2 squared over 2 cubed plus 1, plus when n is 3, 2 cubed over 3 cubed plus 1, etc. Don't forget your plus dot dot dots. That really is essential. If I ask you to write it out the long way, show me the terms, you must put the plus dot dot dots to indicate the pattern continues. This is an infinite series. If you stop it, you've made it be a finite series, which is not what this is about. And yeah, you could go ahead and simplify this. You get 2 over 2 plus 4 over 9 plus 8 over 28, etc. You could continue simplifying that, get 1 plus 4/9 plus, what would it be, 2/7, etc. However, in doing this, though it's good for seeing what the summation equals, it's not really giving you insight into whether it converges or not. Maybe a tiny bit, but it could be misleading. It looks like these terms are getting smaller and smaller. After all, 4/9 is 0.444 repeating. 2/7 is in the ballpark of 0.29. It might seem like we possibly could have convergence, but it doesn't converge. Look at these terms. That's an right there. Look at the numerator and denominator of that fraction. It's not going to 0, right? 2 to the n is an exponential growth function. N cubed plus 1 is a polynomial. 2 to the n grows to infinity a lot faster than n cubed plus 1 does. An goes to infinity as n goes to infinity. If you really wanted to prove that rigorously, you could use L'Hopital's rule, pretending n is a continuous variable, but that's not really our point here. We know intuitively exponential functions grow a lot faster than polynomials. In particular, an does not go to 0. Remember, there's a divergence test. I talked about this on Monday. If the ans don't go to 0, there's no way for the series to converge. Keep track of the distinction between the terms, the ans, and the series, the infinite sum itself. They're related, but technically different. Even if an approaches 1, that would be something non-zero, but the series would still diverge. As an example of that, the summation n goes from 1 to infinity of n over n plus 1. The ans go to 1. The terms converge to 1, but the series diverges. The infinite sum diverges because the terms, the ans, are not going to 0. They're going to 1. It's like in the end, you're computing a bunch of 1 plus 1s plus 1s plus 1s. The series with the summation sign does not converge. And this one does not converge. Therefore, the series does not converge. I could write does not converge, or more quickly, I could say diverges. Okay, those mean the same thing. All right, so the divergence test is really, in general, the first thing you should think about. Now, some problems are phrased in such a way that they say, hey, use the ratio test, or use the comparison test. But when you are not told what test to use, the divergence test is really always the first thing you should think about. And it really is the easiest test to use, at least if your ans are fairly simple to think about. Okay. If they don't go to 0, there's no way that the series converges. What if we had tried to use the ratio test here? What if we had tried thinking about the absolute value of an plus 1 over the absolute value of an, and letting n go to infinity for that ratio. This is the ratio test now. It says if that sequence converges to a number less than 1, then the series, the infinite sum, converges. If this sequence converges to a number bigger than 1, then the series diverges. If this converges to 1 itself, the ratio test provides no information. The series might converge, it might diverge. The ratio test, while it is often helpful, is not always helpful. Sometimes you get a limit of 1 here, and it doesn't tell you what goes on. You might also wonder what happens when the limit of this doesn't exist, and that's a bit more complicated. We don't go into that. But what does this equal in this case? The ANs, again, are 2 to the n over n cubed plus 1. So an plus 1 is going to be what I get when I replace each n by n plus 1, giving me 2 to the n plus 1 over n plus 1 quantity cubed plus 1. And the an is the same thing except use n's. Now there's absolute value signs in here, and we always sort of like, can I get rid of the absolute value signs? Sometimes yes, sometimes no. Here you can. You can get rid of those because everything's positive. I also have the ratio of 2 fractions. I can multiply by the reciprocal of the one on the bottom by what you learned about dividing fractions in 4th, 5th, 6th grade. Okay. Try to simplify. This simplifies to 2 times 2 to the n. So the 2 to the n's cancel. And you are left with a 2 on the top, but also times n cubed plus 1 is 2n cubed plus 2. On the bottom, you could expand n plus 1 quantity cubed, but you don't have to. You can just leave it as it is. Save some time. But now you need to think. That's a rational function of n. You could pretend it was an x instead of an n. Let n go to infinity. What's the limit? Does it exist? The numerator and the denominator have the same degree, 3. So you've learned in the past that when that happens, as the variable goes to infinity, you're going to approach the ratio of the leading coefficients. 2 in front of the n cubed on top, and there would be a 1 in front of the n cubed on the bottom if you expanded this out. It approaches 2 as n goes to infinity. And 2 is bigger than 1. Therefore, the series also is confirmed to diverge by the ratio test. Okay, with the original example, with the original test I used was the divergence test. It diverged by the divergence test. I didn't write that, but that's what I used. Here it diverges by the ratio test. Is it possible that we ever could have gotten an inconclusive answer with the ratio test? The answer is yes. In fact, P series, where you're adding up 1 over n to the p, if you try to apply the ratio test to that, you'll always get 1 for the limit of the sequence. And the ratio test will be inconclusive. But we know from the integral test that P series converge when P is bigger than 1 and diverge when P is less than or equal to 1. We know that. Take that to the bank. The ratio test is not helpful with P series.